Hello and welcome to this week's episode of Qiskit Seminar Series. I'm your host, Alireza Seif. I'm tuning from College Park, Maryland. And yeah, let's give everyone some time to join. And yeah, please use the chat function to tell us where you're tuning from. And as always, during the talk, please ask your questions using the chat. And I'll ask them during the talk. All right. Okay. So maybe let's give it one more minute and then we'll begin. Okay. So we're very excited to have Peter Zoller with us today. Peter is a professor of theoretical physics at the University of Innsbruck and also a scientific director at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences. His work addresses problems at the interface of quantum optics, quantum information theory, and many-body physics. And he's known for many things. Among of them is the proposal for trap-down quantum computing and quantum simulations with atomic platform. He has also won numerous awards that will probably take the full hour to go through all of them. But I can mention the Max Planck Medal, Dirac Medal, the Wolf Prize in Physics, and John Stuart Bell Prize. With that, Peter, please take it away.
Okay, so should I leave on my camera now or should I turn it off due to the bandwidth? Yeah. Can you hear me clearly?
Yeah, we hear you clearly.
Okay, very good. So thank you, Alireza, for introducing me. It's a pleasure to give a talk here in this prestigious series of quantum information seminars. And I will speak today about work which is joint theory experimental work together with my colleague Rainer Blatt here in Innsbruck. And it has to do with quantum simulation. And let me just introduce the topic that I will talk about, in the first few slides, and then we get to the actual point of what we would like to do. I guess all of you are very familiar, with quantum simulation per se, and that why we are running these quantum simulations on quantum machines, real quantum devices. And what we do on a quantum simulator is that we are trying to solve a quantum many-body problem. The example could be from quantum chemistry to quantum materials to some condensed matter problems, or maybe even a lattice gauge theory, and so on. And what we do in this context is that we always write down a Hamiltonian, the physics Hamiltonian that we have. I'm symbolizing this here just with a Heisenberg model. And instead of then going to a classical computer, we try to simulate this on a quantum machine, either as an analog simulation, digital simulation, or maybe some sort of a hybrid, which is between analog and somehow digital. And the reason why we do that is this, that quantum mechanical machines have entanglement. I mean, this is the reason why we are using this. This is the challenge also for classical computation. And this is the reason why there's an advantage in using a quantum device for the simulations. But at the core, of course, of all of these discussions is the entanglement per se. And what my talk will be about is this, that we would like to learn about entanglement, as it is present in quantum simulators and quantum simulating devices as a many-body problem. And we would like to learn entanglement maybe in more detail and maybe also in somewhat a different form as we normally do when we just look at, like in condensed matter physics, at some low-order correlation functions and so on. So the topic of the talk at the end will be goal and challenge, learn the entanglement structure of the many-body wave function, hopefully in quite some detail beyond what one normally does. And to be a little bit more precise, so this goal and challenge, learn the entanglement structure. Quantum simulation, somehow among the quantum problems, is somehow very special, because what we have there is local Hamiltonians, and this locality of the Hamiltonian has a lot of consequences. And in the following, what we are going to do is this, that we would like to think about, or the meaning and learn about entanglement with these local Hamiltonians. And we will try to do it from actually two perspectives. First one, we would like to identify certain, let me call it, universal or generic features of entanglement of the many-body physics, which is very much related to the locality of this Hamiltonian. And number two, what we would like to do is this, to develop protocols, quantum protocols, sort of quantum algorithms or circuits, you might call it, that run on today's NISQ simulators, noisy intermediate scale quantum devices. And we want these algorithms to be scalable to large particle numbers. I mean, scalable in my context here means that we would like to do it in a domain that is feasible, where we are able to display things like, you will afterwards see that we're able to do a quantum state tomography in some of these cases, going to more than, say, 20 particles and so on, which is really quite large. And we can do that, of course, due to the locality of the Hamiltonian that gives us extra tools to do some of these things. And I would like to emphasize that these protocols that we are talking about, that we would like to develop, that are scalable, and I quote here, going to large particle numbers, we would like them at the end to operate in high dimensional settings. I will talk about ions in the following, which is basically 1D, but they also work for Rydberg arrays, for example, where we have a priori 2D, or maybe also optical lattices and so on. And eventually also in the regime of a quantum advantage, where some of these computations are hard to do as classical post-processing. And so in that sense, these algorithms that we will talk about, or the study of entanglement, will be rather generic. We are setting up tools that are hopefully very useful in a very broad context. So in this sense, this leads me then to the first slide of my talk here, which is, I called the talk here, Learning Entanglement in Quantum Simulation. And I'm playing here, of course, with the word learning, because, you would like to learn something as a physicist, but there's also this notion of machine learning. And you will see in the following that we are sort of learning, we're doing Hamiltonian learning, we're doing entanglement Hamiltonian learning, and these kind of things. And for the systems indicated down there, I sort of have here just a list of my favorite quantum simulators from an AMO context. Programmable quantum simulators as atomic NIST devices, from trapped ions, optical lattices, Rydberg arrays, polar molecules, and also cavity QED. And this is sort of the setting, the experimental setting they'll be interested in. The important point in the following discussion is that these quantum simulators are actually pretty scalable, to very large particle numbers, much more than sort of the standard universal quantum computers that we normally talk about. But they also have a certain amount of programmability, which might not be universal and may be sort of very special, but sort of this combination of scalability and programmability, I would say, is the unique feature of the experimental setting that we are interested now in the following, and that we are going to play our game of learning this entanglement. In this talk, I will very specifically speak also about trapped ions for the reason that we have a great collaboration here with my experimental colleagues, Christian Roos and also Rainer Platt, where we have a local trapped ion quantum simulator that we as theorists are allowed to play with. And I will show you afterwards experiments that we are doing. So the work right now sort of happens in the form where we not only develop now maybe some theoretical algorithms as being theorists, but we also try to play directly on the quantum machines that are available to us to do these things in very close collaboration with the experimental friends. Okay, here's some nice pictures about the kind of platforms again, and about kind of recent papers from Rydberg atoms, Hubbard models, superconducting qubits, trapped ions. The kind of things that I will talk about in principle apply to all of these different platforms that we have over here. But as I said before, I'll be mainly interested in the ions, because this is the experimental setup that we have direct access to now, the following. Okay, to be a little bit more specific, the programmable analog simulators that we are talking about, I give you here two examples. On the right-hand side is a trapped ions that I've mentioned now several times. And very specifically, the setup that we have here that works in 1D, but sort of 2D versions are also now coming online, is that we have a string of iron indicated over here, storing spins. They represent spin 1/2 in our case, so just a qubit, spin up and spin down. And if you go through the derivation, this is sort of standard stuff in the context of trapped ions, you find at the end that the Hamiltonian governing this thing here, when you shine on some laser lights that are tuned in an appropriate way, can be understood as an Ising model down here, an Ising model that has long-range interactions. All of these parameters are in principle tunable, with something which is an effective transverse field here. And the whole thing is programmable to the extent that we can, of course, take laser light and shine it on individual ions, either to manipulate them or to read them out. And I would say Rydberg's, at least in the 1D configuration I'm drawing here, are actually very, very similar conceptually. There, what we do is this, that we have an atom in maybe a ground state, but we can excite them to Rydberg state and get corresponding then spin-spin interactions that are written as the Hamiltonian that we have down here. So we have here a setting where we have individual addressability and also individual readout, but we have sort of, big entangling Hamiltonians given by an Ising model or by the model that we write here for the Rydberg atoms on the left-hand side. And as I said before, the unique feature for these systems as a playground is that they can involve quite a large number of particles, but the reduced programmability, you should understand here that, well, we just have the Ising Hamiltonian, for example, in the ions, and then we have single particle rotations, and this is then the playground to do the kind of games and protocols that we would like to do, hopefully getting away with some low-depth circuit for the things that we would like to measure at the very end. So this is, a picture from the lab that I got from Rainer Blatt some time ago, indicating the 51 ions downstairs. This is the setting that we will now consider in the following. But let me start out by maybe telling you a little bit about, this experimental device per se and what we can do, sort of to some extent repeating for large particle numbers for what we did earlier. And then I will become very concrete and talk about, the ideas and protocols and corresponding experiments that have to do with learning about this entanglement, as I indicated before. So take the following few slides more as a technology statement. What we are going to do is this, that we will talk about variational quantum eigensolver. We will choose certain Hamiltonians like the Heisenberg model, and then ask if we can prepare for 51 ions approximate ground states. I mean, we cannot get real ground states there, of course, but we got approximate ground states, and they will then provide us, with entangled states whose entanglement properties we would like to investigate on a rather sophisticated level. So some of the sort of technical tools on the theory side were developed and also experimentally, were developed in a paper that we wrote now a few years ago. It was called Self-Verifying Variational Quantum Simulation. And just from the photograph that you can see over here, you can see that this is a mixture, hopefully coherent superposition of theories like Christian Cockell on the right and Rick van Bijnen on the left, Christine de Meyer in the middle as the experimentalist. And at that point, what we learned, we call this thing variational quantum simulation, is, for example, to play games like VQE, preparing ground states like for a Schwinger model or whatever, doing lattice gauge theories and so on and so on. And the specific topic at that point was self-verification. I mentioned this with one slide. And there was a whole setting developed. And now what we would like to do is we would like to go from 20 ions earlier now to the 50 ions and sort of see to what extent we can actually repeat that, because the kind of things that we would like to do in physics then afterwards will be very much related to being able to do this preparation of quantum states. And then what we're really interested in, the following measurement protocols for a very large number of particles. Normally, what you do in a quantum simulator, analog simulator, like the one that I showed to you, either with ions or maybe Rydberg's, is that you can prepare some initial state, like a product state, have some quench dynamics producing an entangled state psi, And of course, we can make our individual measurements, reading out single shot measurements, these qubits or spin configurations that we have, resulting then at the end in some, probabilities that you want. This would allow you then to calculate correlation functions. What we want to do is actually, as I said before, a little bit different stuff, because we would like to take these beautiful Ising interactions as sort of huge many-body 51 ion entangling circuit. It's like a big circuit which has a very special form, namely the one given by this Hamiltonian that we have down here with this finite range interaction. This parameter alpha I mentioned before is something like maybe 1.2 or so. And then what we can do is this, that we can take these entangling operations and we can apply them several times, interspersed, for example, with single particle rotations. And if you do a circuit like this, a low depth circuit, you can see right away that we get here families of entangled states that are parametrized by these angles that I call here theta 1 to theta n. This is the parameter set. And you can see that from these arguments here, I'm sort of setting up now a VQE wave function. And these are the ones that we can do in the lab, with a significant fidelity, and this is then really look at these entangling operations here, sort of doing in a single shot, the 51 ion entangling gate of a very specific form, but of a form that can be done with a rather high fidelity. Well, as I said before, we would like to do now the game of VQE, variational quantum eigensolver, to prepare, for example, ground state of certain Hamiltonians. And let me just remind you how this works. We have here on the left-hand side our gate set, a very special gate set for these programmable simulators, and the classical compute on the right-hand side. And what you would like to do in this variational classical quantum algorithm is that you take in the present case over here, an energy, just as the expectation value of a target Hamiltonian that you picked, and you write down on a piece of paper your target Hamiltonian that you can see on the left-hand side is maybe something having 1, 2 body interactions, 3 body interactions, whatever. For us at the end, it will be the Heisenberg model for today, but we can, change that, of course, to a different system if you want to. And then what you do in that case here is this, that you run this feedback loop that you have here. This is standard VQE, so there's not much to be explained, that we have here to measure expectation values, 1 particle correlators, 2 particle correlators, and so on, to finally define this energy landscape over here. And the great thing about, and this is why we sort of fell in love with this variational stuff, is that these kind of circuits, you might not know all of the details in terms of process tomography, but you don't have to know, because the whole thing is very robust towards calibration errors that you have. And so from that point of view, if you want to go to a very large particle number, this is an ideal setting that you have in terms of robustness to, for example, calibration errors and so on. Well, I mentioned before that, it's now a few years ago that we developed these things first for the 20 ions, doing VQE cooling, and this was the lattice Schwinger model. I'm not going to tell you the physics over here. It was a lattice Schwinger model. We converted this thing with the Jordan-Wigner transformation to a spin model here. The spin model was really, really ugly. I mean, I write it down over here. And then we came up, also with a way of, because it's called a dividing rectangle search. This is a global optimization algorithm, for the parameters that we have in our case that we would like to optimize. And what we learned at that point is that we can globally, this is what the search algorithm is, with 50 parameters, and go to a circuit depth of something like 6 and about 10 to the 5 calls to the quantum simulator, get actually very close to the ground state for the 20 ions, clearly resolved from the first excited state. We could measure that, experimentally, and also compute these things theoretically. There was perfect agreement. At that point, the highlight was, of course, the self-verification that on this quantum machine, you not only prepare this approximate ground state, but you can also measure on the quantum machine what the variance is of the Hamiltonian, therefore giving you right away an error bar that you have for the energy. So the machine gives you the energy and also the corresponding error bar. This was the story then. So can we do that also for 51 ions? Okay, so what we want to do now is that we would like to take a model, maybe 31 ions for the start, and let's choose today, and you will see the reason why a little bit later, because we are going to do things like conformal field theory and ground states and vacuum state and corresponding ground states now for many body Hamiltonian. Let's take as a playground now the XXC Heisenberg chain. It's written over here. This is an XX interaction over here. Then we have a CC interaction. If you take delta equal to the J that we have in front, then of course it will be the normal, completely isotropic Heisenberg interaction. I've indicated a phase diagram down here. This is parameter delta, anisotropy. And then we have here a critical regime. We will, for example, then pick, say the point that I'm indicating over here. And you might simply say, well, okay, so let's write down the circuit. You play around a little bit. You do some small numerical simulations. And the expert behind it is Christian Cockale in our group, together with Rick van Bijnen. And then you talk to the experimentalists like Manoj Joshi. And cooking up a circuit. And then you try to run it for about 31 ions, like over here. This is, again, the details of the coolings that are not very interesting. You might ask, how low do we get in energy over here? But let me it's pretty good. But really what we would like to do is to do this for 51 ions. And you can see for 51 ions, we don't really go to the ground state here. And if you analyze it a little bit more closely, then you can see that this VQE with these very short circuits that we do over here goes to something which is, if 51 ions, so Hilbert space is 10 to the power 51, so it's about 10 to the 14. You're in the 2%. If you draw the whole energy spectrum of the Heisenberg model, you are within 2% of the ground state, given that the Heisenberg model has a lower state and a higher state. And I think that's actually pretty good. I mean, so these circuits, even though they're very short, they cool down to very low temperatures, or I shouldn't call it temperature here, because what we produce is really states, superposition states of the maybe 300 lowest eigenstates that we have in our system over here. So this is sort of the experimental setting. This is the starting point of our discussion. And the question is now, what can we do with these kind of things? And then go to the actual topic of, we would like to see what kind of an entanglement that we have produced in the wave function and learn it maybe on the level that so far was not really accessible in the form. So switching now to my real topic of the talk, which is learning entanglement in quantum simulation.
So, can you hear me here?
Yeah.
So there is a question in the chat about the platforms I wanted to bring up before we change topic. So the question is, are the tweezer arrays trapping ions or neutral atoms, and does it matter?
We don't have any tweezer arrays here. So if you take tweezer arrays, you have to take neutral atoms. Here we talk about an ion platform. This is a 51 ion quantum simulator in the way that I indicated it earlier. And if you take, of course, optical tweezers, to trap single atoms, then it would be a Rydberg programmable quantum simulator where interactions are being generated by, taking your laser and then, lifting the electron up to the Rydberg state. And once electrons are in the Rydberg state, then they start to interact over distance, which in this case, maybe something like 10 micrometer to say a number in that case. Okay, so this is really trapped ion quantum simulator where we just store a string of ions in an ion trap, which is a linear Paul trap. And so this gives you the 51 ion strings that are indicated down here. You can see this line down here. These are the 51 ions. And these are the 51 ions that are implementing here the Hamiltonians that I talked about before. Okay, so in that sense, let me now go on to learning entanglement in quantum simulation, become a little bit more precise with what we actually want to measure and why it is actually hard and why we have to come up with special protocols. If I take a many-body system, and let me assume that I prepared the ground state to be specific, and I'm drawing this in 2D to be sort of more general here. If I take out a certain subregion that I have over here, and I call it A, we can introduce a reduced density operator, namely by tracing out in this ground state, in this pure state wave function, the region B, which is the complementary one over here, defining a reduced density operator. Clearly, if this state over here is a pure state, if there's interactions, if there's entanglement, then the rho A that we have here, the reduced density operator, will be mixed. And I guess many of you may be familiar with the fact that we can write down, if you have a many-body wave function over here, what we call a Schmidt decomposition, where we decompose this wave function over something which is a superposition involving region A and B. And here's a sum that's labeled by alpha going up to the high. This sort of tells you if high is equal to 1, this would just be a product state. But the larger the high is over here, this is kind of a measure of the entanglement. This corresponds to the rank of the reduced density matrix that we have over here. And we will be very greedy afterwards and ask things, can we measure, for example, the Schmidt decomposition of ground states, of excited states? See, what the chi is over here, how large the entanglement is in the system. That's the kind of things that we would like to learn. And let me sort of, at the beginning, phrase this slightly different. We could look, for example, and this is kind of the simple version that we'll do and that we have also done in the past, is you could measure, for example, purity. This would be an example of a Raney entanglement entropy. If you measure the purity, if it's equal to 1, you got a product state. If it's less than the 1, this would indicate mixedness, and the mixedness would indicate entanglement entropy, and therefore sort of be a simple measure of the entanglement that we have. But even at this point, you might say, how do we actually measure something like a purity? Well, we've come up with protocols in the past, and if you would like to read it, there's a review that we wrote on what we call randomized measurements together with these people down here. That we developed a toolbox to measure that. I'll come back and explain a few of these things a little bit later. But the challenge is how to measure, and why is this a challenge? Well, you might even then be more greedy and talk about things like a von Neumann entropy, like the one written down here, where you would like to measure then an entropy which is now log of the trace of rho log rho A that we have over here. And again, the question would be how to measure that. These are very complicated nonlinear functions that we have here as a function, of course, of my density matrix that I have. Let me also introduce another quantity that will be very interesting now for the following discussion. Of course, if I got the reduced density matrix, I can always write it as an e to the minus h, and I will call h here the entanglement Hamiltonian. You can see that the mixed state that comes by tracing out part of the system has now an entanglement Hamiltonian here. And if you ask afterwards, what is the reduced density operator, we can equally talk about that by sort of knowing what the corresponding entanglement Hamiltonian is. These entanglement Hamiltonians have a lot of very, very special properties, and we are going to play this game now in the following. Notice that formally we can really see that this, by writing it in this form, this has a form of a Gibbs ensemble, where sort of the entanglement Hamiltonian is the one which is generating the density operators corresponding to this Gibbs ensemble. And so you might say at that point, if I would like to know something like von Neumann entropy, or maybe the entanglement spectrum, like the eigenvalues of this entanglement Hamiltonian, and learn, what the rank of your density matrix is, maybe we should work, by trying to find out what the operator structure is of the entanglement Hamiltonian. We should learn the operator structure of the entanglement Hamiltonian. And if you want to know what the eigenvalues are, we should be able to do something like an entanglement spectroscopy. And based on that, you would then be able to answer interesting things, hopefully for very large subsystem sizes. And that's what we're going to do in the following. So here's a formal definition of this entanglement spectrum. That if you take the density matrix and you diagonalize it, you can see that these are the corresponding eigenvalues that you have over here. And we call this thing the entanglement spectrum. And we are going to ask, can we also measure that? Why we want to do that? Well, I'm not going to talk about topology here, but if you read papers by Nobel Prize winner Duncan Haldane, he will tell you about that measuring the entanglement spectrum in topology, where you might find certain degenerates and so on, is a very sophisticated way of classifying and also understanding topological phases. We will do something a little bit different here, but let me at this point just mention or emphasize why it is hard to measure this density matrix or this entanglement Hamiltonian in general. It simply has to do with the fact that I guess all of us know that if you do quantum state tomography, that it is very expensive because it scales exponentially with the system size, with the number of particles that you have. So doing tomography to find then out what the rho A is something which is you can do only for very, very small system sizes. Or this is the alternative, and you probably already guessed what you're going to do now. If you know something about the structure of the density matrix, or in the case afterwards, the structure of the entanglement Hamiltonian. If you got certain quantum states that you want like to investigate, where maybe this entanglement Hamiltonian has a very simple operator structure, then you might be in business and doing a quantum state tomography for much, much larger subsystem sizes than you might be able to do if you know nothing, and you have to do just a plain tomography that we know so well and is very inefficient and very expensive to do. And you might say at this point, so what do we know now about the state? Well, the answer is that we are doing quantum simulation. So we know that the states that we are talking about over here, that is reduced density matrix, sort of goes back originally to the fact that we had a local Hamiltonian, not entanglement Hamiltonian, local Hamiltonian that gave rise to these states. And it is quite amazing that the locality of the Hamiltonian that gave rise to the quantum states that we have over here sort of leaves its trademarks, in the fact that actually that this entanglement Hamiltonian over here has a much simpler structure than the most general case. And this is exactly the topic or the question of interest that we are going to investigate now in the following. Okay, so what do we know and what does it mean? So let me remind you, probably most of you have never heard that. There's something in relativistic quantum field theory. This is very mathematical, goes back a long time. And there's mathematical theorems have been proven in this context, where the statement is the following. And this is statement, I find it very remarkable that we're going to translate afterwards to many body systems. And the statement is basically the following. Imagine that you have a relativistic quantum field theory. So this means that you write down here Hamiltonian density, you integrate over space. And you can see on the right-hand side, we're going to divide then afterwards space into A and B in the region. So we have here a relativistic quantum field theory. Relativistic means that the theory should be Lorentz invariant. And of course, this theory has a ground state. It can be a very complex theory, very complicated. It has a vacuum ground state. The remarkable thing is, and this is, was invented by Bisognano-Wichmann and then in Conformal Field Theory by these guys over here. It is reviewed in this excellent review, recently written by Marcello Belmonte and friends, that if you would like to find for the ground state over here, the entanglement Hamiltonian, there's a very, very simple answer. Even though it's universally valid, modulo, of course, the fact that we need a relativistic quantum theory. And this is the following one. If I take the vacuum state, the ground state of a relativistic quantum field theory, and I bipartition it into A and B, I'm drawing this here one-dimensional, but you can also think about this thing being high-dimensional, just dividing the space, in A and B. The remarkable thing is that the reduced density matrix of the vacuum state, without making any further assumptions about, how complicated interacting your theory is, can always be written as a Gibbs ensemble. You can see this is exponent of, read this beta here as a temperature times h. So if beta was a constant over here, if we can pull it out of the integral, this object here would be the Hamiltonian. This would be like a normal Gibbs ensemble, like we know from thermodynamics. But no, in the present case, this is the vacuum, this is a ground state. It turns out that this nonetheless is this structure, but this beta of x that we have over here is a local inverse temperature. So the remarkable statement is that the reduced density matrix is a Gibbs ensemble, but with the local density operator, with the local inverse temperature. And of course, this whole object up here defines the Hamiltonian. And if you look at what this temperature dependence is, it again has a very intuitive meaning, because this inverse temperature has the form of a ramp. It sort of goes up here. So here the inverse temperature is very small. It means that the system is very hot, and that's very intuitive, because if a system hot, it means that locally the density matrix is very mixed, because the particles are entangled across the cut that you have over here. And if you move away from the cut, then the temperature gets lower and lower and lower. It gets less and less mixed, and this is exactly written over here in this form. Remarkably, this is a theorem in relativistic quantum field theory. So the statement is that the entanglement Hamiltonian in that form has a remarkably simple structure. It is just the old Hamiltonian, but sort of the Hamiltonian density, multiplied by this ramp over here, by this inverse temperature, which is now space dependent. And this is extremely simple. And if you generalize this to conformal field theory, you might take a region from the bulk over here, like in the center, that is beta of x, this inverse temperature, is the form of a parabola. We'll see that now in the following quite often. Again, it's the same formula as before. And again, this was proven in some of these papers down here, in the context of conformal field theory, actually valid here, not only in one dimension or 1 + 1 dimensions, but also in higher dimensions. Okay. So having read this thing, you might ask yourself, can we apply this theorem to something like lattice models? And of course, once you talk about lattice models, it's no longer a theorem. But let's sort of try to adapt it and maybe use this as a guideline for our entanglement study, when at the end we would like to learn the entanglement Hamiltonian. So if I take a lattice over here, I'm just drawing a 1D model here, and I divide it into A and B, then the statement basically is, if I just adapt, what I said before, that the entanglement Hamiltonian, this rho A is the reduced density matrix of the subsystem here, has this form H tilde, and H tilde A, I can simply get, well, write down the Hamiltonian on the lattice. This is the upper line over here. And then what you do is you get the entanglement Hamiltonian here, basically by just taking these bits and pieces that you write up here, but you multiply them by a local temperature or inverse temperature that you call a beta L. So in other words, the entanglement Hamiltonian is just a deformation, you might call it, of the original Hamiltonian, plus there will be certain corrections, okay? And you might ask, how good is this thing over here? And this is what we are going to explore now in the following, including experiments, okay? So the first thing that you bring up, of course, will be, you talked about relativistic quantum field theory that has Lorentz invariance, and at the end you apply to lattice models and you do ground states rather than the vacuum. Is the whole thing still valid? And there's remarkable evidence, and this has been studied quite in detail in the literature, to what extent this simple sort of rewriting over here is valid. There's certain analytical solvable models where you can also do that, like in the case of the Ising model. And we have a lot of numerical evidence. And I just show you one example. We talked before about the Heisenberg model in 1D. And if you do DMRG and you try to see, is the entanglement Hamiltonian like that, you indeed find the entanglement Hamiltonian has a very high accuracy. This parabolic structure, is exactly the parabolas I talked about. And this is the inverse temperature that we have over here. And second, you can also see that I talked before about, can we do tomography? And my answer was, we can do tomography provided we know something about the reduced density matrix and the entanglement Hamiltonian. Now we have an idea, what it can be, and we can make an answer like this. But of course, we then have to fit these parameters, but then at the end also verify these ansatz by checking if you got additional terms over here. So to what extent this Hamiltonian, this entanglement Hamiltonian with this Bisognano-Wichmann type ansatz really, is the one that you have in a many-body state for the ground state. We have to develop tools for actually measuring that. So to elaborate on the second point over here, we have in the past developed, around this paradigm that you simply say, I got the measurement data, taken an experiment by making measurements of the ground state over here, taking measurement data, by fitting it to an reduced density matrix that you write as an entanglement Hamiltonian, and the entanglement Hamiltonian up there, you write as an ansatz suggested by Bisognano and Wichmann, and you can see what the point is. This entanglement Hamiltonian only has a polynomial number of parameters over here, plus maybe additional ones over here, polynomial number, and this makes a very efficient ansatz. So from relatively few data, you might be able to infer this GL or this beta L coefficients that we have here. And I try to indicate this down here. You design a certain ansatz based on what you think it is, if data to fit this thing, you get the entanglement Hamiltonian out. Most important, of course, in this context is it's not that you stop at that point and you believe it. Then you have to take more data and you have to do a verification step where you have to see to what extent the Hamiltonian that you learned over here, really overlaps, with the effective density matrix that you construct from this more data. So there's you learn the Hamiltonian, and there's a verification step that sort of verifies that indeed, that the fidelity of the new data set that you took, with the previous one, that hopefully this is close to 1. Ideas like this were developed in this paper. So we had a Nature Physics paper where we wrote out all the details behind that, and this is a lot of technicalities, but I guess you got sort of the basic idea. What you're now going to do is this, that we are going to apply these ideas now in a very specific setting, and we are going to do that now also with our quantum simulator, implementing these protocols and trying to find the entanglement Hamiltonian, and in particular this very curious thing that the ground state, for example, if you are at the critical point, is supposed to have an entanglement Hamiltonian, which is basically like a finite, like a Gibbs ensemble with an inverse temperature, which has the form of a parabola. But let me put this thing right away a little bit more general, and sort of let's lead the discussion as follows. So we have here a many-body problem, and on the left that you choose. And as I said before, in our case, it will be the Heisenberg model. Heisenberg model, again, we have a gapless phase over here. There's a gap phase here. We go, for example, to the point indicated over here, maybe another one then over here. We know how to prepare, approximately at least, ground states for this, with pretty good accuracy. As I said, these 2% that you saw before. And on the right-hand side, I've drawn here in a somewhat symbolic way the energy spectrum of my many-body system. And according to our discussion we just had, we might prepare, for example, a ground state, or I should call it approximate ground state over here. But we might also prepare an excited state. I'm indicating one state and one state down here. Actually, that's not true. It will be a whole band, and you will see that immediately what it is. But what is now sort of for the ground state, but also then for the excited state, my reduced density matrix or my corresponding entanglement Hamiltonian. Let me first of all remind you that if you talk about ground states of these many-body systems, due to the fact that we have the local Hamiltonians, we know that the entanglement entropy, the von Neumann entropy, obeys something that we call the area law, namely it scales like the dimension. In our case, it's just the linear dimension of the subsystem to the power d. D is in our case here 1. It's a one-dimensional system, but the formula, of course, is valid also in higher d. If you have a CFD, then there would be a logarithmic correction with a central charge. So for the ground state, we would expect that the entanglement, has this particular form displaying an area law. And if you go to the excited state, we have here a volume law. You can see we had the d-1 and up here d. This is what you know from a thermal entropy. This is sort of the volume law scaling like we know in thermodynamics. And of course, the ground states are in a very small corner of the Hilbert space over here, whereas, of course, these many excited states that we have will show this volume law entangled there. Most of the states that we'll find here correspond to these eigenstates. They will actually be volume law entangled. Just one minor remark. Of course, area law is just the reason why in the ground state, we can do, for example, here MPS, or tensor networks. This is just based on the fact that we have area law, and then in this sense, very little entanglement. Whereas in the excited state, of course, a quantum simulator doesn't really have any problems representing area volume law states, sort of almost by construction, we'll say, because it is a quantum system. So let me start now, sort of continue here. Suppose that we prepared an excited state, or maybe a superposition of some of the excited states, and rho A is the density matrix. If I take an excited state here and just sort of appeal for the moment to something like an eigenstate thermalization hypothesis, you would have here a reduced density operator, and all of you would probably guess right away what the reduced density operator is. Well, reduced density operator, if I take a subsystem out from one of the eigenstates, would be basically a thermal state. So it would be e to the minus beta, h now being the Hamiltonian over here. So this is a thermal Gibbs state, and you can see this looks very similar to the entanglement Hamiltonian that we had before, except that for the ground state, we wrote this beta inside, that was an index I. If it is a thermal state, that the beta is the temperature of my system. And this is sort of this is my thermal state, my thermal Gibbs state. Plus, of course, there will be certain boundary connections over here that I'm not writing here. If you allow me to graphically represent the thermal state here, I would do it like that. I would simply say, let me plot here the local temperature. Well, the local temperature for a Gibbs state, high temperature is constant. This is what thermodynamics tells you. So it's flat over here. And you might then sort of do these things now for different system sizes. If you take a state like the one over here, the thermal state, and you work out what the entanglement entropy, of course, it shows volume law entanglement, which in 1D is just a linear line here with the LA that we have over here. This is a thermal Gibbs state. So what happens now when you cool sort of the quotes, to the ground state, and you do the same thing for the ground state? Well, I actually just gave you the answer. Bisognano-Wichmann tells you that the ground state, on conformal field theory, at least when it's valid, the inverse temperature should be of a form of a parabola. So there's a very dramatic prediction, which is rather universal, actually, namely that if I highly excited state, I take a subsystem out, it should be thermal, constant temperature. If I go to the ground state, I should see a parabola. And of course, I should see area law. And if I'm at the critical point, of course, there will be over here then also some logarithmic correction. So this would be area law. So you can see that we see a volume law to area law, and it's sort of reflected in the entanglement Hamiltonians that we have in our system. And if you do a little bit numerics here, you might simply take your Heisenberg Hamiltonian over here and calculate for the ground state. I've shown you this plot before. You see the beautiful parameters over here and this logarithmic dependence for the excited state here. You have a thermal distribution. You can see slight deviations at the edge over here, but basically this thing is flat. And then the volume law entanglement is what you calculate numerically. So the question is, can we see that in an experiment? We have developed the tools, we have prepared the proximal ground state. It's not the real ground state, but we are pretty close, And we have developed tools to do an entanglement Hamiltonian tomography, based on the ansatz guided by Bisognano-Wichmann, if you believe these kind of things that I talked earlier. And can we see that? And let me show you the results, okay? And then we will afterwards, do a little bit more depth explaining some of that. I show you results now from doing an experiment. And the experiment starts out by preparing an Heisenberg ground state, at the critical point. And we do that. This is the XXC chain over here. For example, by having a phase diagram, we could take delta equal to 1, that's a critical point, or we could also actually go away to 1.7. That's also what we are doing in the following. Here's 51 ions. You take a certain subregion out here. And then we sort of say, well, Bisognano-Wichmann tells us that the reduced density matrix should have the form of an entanglement Hamiltonian, which simply has these local temperatures, inverse temperatures that we talked about here before. And this should be a zero-order ansatz if you want. So on the left-hand side, you can see my energy spectrum now again. So what we do now is this, that here's sort of how the experiment proceeds. First of all, you write down a VQE circuit. We talked about that before. VQE produces on one hand an approximate ground state. This is the blue one, and I indicated down here by this region. This is roughly the superposition that we get with our kind of hack, to produce an approximate ground state. But you might also make a VQE to an excited state. I mean, it will not be very good. We're far away from a single eigenstate, but you can see it will be a certain region. Here we are about 40% up in the energy spectrum, and down here, we are much, much lower. This is 0.02, so but we have about 2% of the total energy range of our system over here. This is what we're able to prepare an experiment. And now let me show you results, what I get out, and I will afterwards show you how we actually obtained them. So if I go to the critical point, conformal field theory should be valid. If I plot here the entanglement entropy, you can see the S von Neumann entropy. We know the entanglement Hamiltonian. We can fit all of that. We can see for the thermal state up here, a beautiful volume law entanglement. And we can do that actually for subsystem sizes. You will see it on the next one that go up to 20. And this is really, really huge. This means that we're able to do an entanglement Hamiltonian tomography, or a tomography of the very particular states that we have over here, for up to 20 lattice sites. Down here is the area law. You can see you go to the ground state down here, it's flat. So you can see here the crossover from an area law to a volume law entanglement. And if you would like to see what these inverse temperatures that I talked about earlier are, you can see that the ground state shows, this is for 12 lattice sites, a very beautiful parabola over here. Whereas the excited state is kind of flat. I mean, we are not really completely thermal here because it's like, heated up sort of, with your circuit. And, but clearly this is flat. And notice that there's actually a different energy scale over here. So actually this thing is very, very mixed. It should be all the way down here. So we multiply this by a factor, and you will see now, when we go to 1.7, away, this is sort of more the product type state that you would, when you go away to the critical point, you can see that the volume law is again here, and then there's area law for the ground state. For this inverse temperature argument, there's no conformal field theory argument. This is a beautiful parabola on the right-hand side over here. And some theory papers predict that actually it's more a triangular form rather than the parabola that we have over here. And you can also see here now this different inverse temperature scale that we have now for these red ones over here that correspond to a thermal state. I think that this picture, my opinion, I mean, I'm super excited. It took us 1.5 years to work, get all of these things going, as a combination of theoretical algorithms implemented in the lab, and then of course experimental art, and actually doing that in the group of Rainer Blatt and Christian Roos. We really see area law to volume law, transition. Of course, if I go to 1.7, there's less entanglement. Indeed, the slope is lower. And if you do a theory curve, actually it is the line that you have over here, this solid line. And I will show you on the next slide now, what is much more detailed, what these inverse temperatures are for ground and in excited state, and for what system sizes we can actually do that. And I think that this is the first observation here, experimental observation of these predictions for ground states of Bisognano-Wichmann, or actually here in the context of the conformal field theory, where these things are valid in the bulk of our system. And again, there's a 51 line simulator, and then subsystem sizes over here for 12, and this is then very near. Sorry. Yeah.
Can I interrupt you and ask some questions from the audience? There are many questions there. Yeah, so I guess one question is, what kind of physics problems do these simulations help solve, or like what phenomena maybe these you can study with these? What questions can you answer? So this is one question.
Yeah. Okay.
Yeah.
So the question is, why the hell do we care about measuring entanglement and then entanglement Hamiltonians? Okay. And I would say that the fact that, for example, we get this parabolic dependence, it is an amazing statement that the reduced density matrix of an many-body system, how complicated it is. Well, it needs to satisfy a certain requirement, like the emergent field theory has to be show Lorentz invariance, or then the critical point, it will be conformal field theory. That the entanglement Hamiltonian, has this very, very simple structure, and that the transition between the, parabola over here and that you have a thermostat where the whole thing is flat, incorporates the whole information about going from an area law all the way to the volume law. So we are really looking at the details of the many-body wave function of the ground state far beyond any low-level correlation functions. We are basically doing a we are measuring the Schmidt decomposition of the many-body ground state, and we find properties like these parabolas over here that we believe are very universal across, all of the different models, within the validity, of course, regimes here, are sort of universal statements about entanglement of ground states versus excited states in a many-body system that we can explore in this context. So I think it is a very fundamental phenomenon that we see it here for the first time. And I mentioned before that if you would like to do a measure, we know sort of to measure now the entanglement Hamiltonian, the operator structure in a many-body system on our quantum simulators for pretty large system sizes. And if you believe Duncan Haldane, like, for example, in the context of topology, and I will show you afterwards also example in the context of quench dynamics, this provides us, with a complete description, of many phenomena. Like if you see degeneracy in the entanglement spectrum, it is an indicator of topology and the unique signature of topological phases in a way that was inaccessible so far. There was a second question? Or?
The second question is, so they're asking, so the Bisognano-Wichmann theorem is originally stated in terms of modular groups and Poincare invariance, but now you're presenting a very nice and simple picture. Is there an understanding of how this simple picture emerges from those abstract theoretical ideas?
The answer is sort of yes and no. I told you before that there's this nice review by Marcello Dal Monte and friends. And there's a group of authors there that incorporate mathematicians, they talk about modular Hamiltonians and about serious mathematics in the background coming from quantum field theory, where these things are proven as mathematical theorems. And then confronting, with special analytical solvable models, these predictions, if you just put them naively on the lattice, or then doing a lot of numerics and testing these things. And the conclusion from all of that is that to zero order, this sort of naive extrapolation to a lattice, seems to work. If somebody would like to understand, the details, what these corrections are, and many of them will be non-universal corrections, I would say that this understanding at the moment is not here. But the attitude that we are taking in this context here is this, that, well, we can produce these machines and these quantum states in our machines. We can try that as an ansatz, and we can see if we put in additional terms beyond this Bisognano-Wichmann, if they're there. And, within the error bars, we do not see them. So the statement is that we get remarkable, agreement with something where I think a lot of theory still has to be done to explain some of these corrections that I talked about. But I would say that we have now a playground, where exactly the question that you're asking, the zero order conformal field theory, for example, makes a prediction. How well is this, approximated in our lattice models? The answer to zero order is really, really good. But there's a lot of details, and we have now, I think, the handle to investigate these things. And this is both theoretical and also experimental work, which is necessary. But maybe first of all, theoretical, I would say.
I see. And just a very short question. These are experimental results, I assume, on trapped ion, on the same trapped ion system that you showed?
Yes, that's right. So I showed you before, you take 51 trapped ions, you make an approximate ground state, by putting in a BQE with the Heisenberg Hamiltonian. You get the 51 ion entangled state, and then you run your sort of, entanglement Hamiltonian tomography. What comes out then is exactly the Bisognano-Wichmann type of predictions over here with very high accuracy that include also all of these things like volume to area law entanglement in a way that I guess has never been seen before. Yeah.
Thanks.
That's sort of the statement. So if I take now this sort of Bisognano-Wichmann story a little bit more accurate over here, and I show now more results, you can see that this is now indicating really the energy distribution, the ground state over here that we really have in the experiment. And this is now a fit to this Bisognano-Wichmann suggested ansatz, where you really leave open as variational parameters or parameters to be adjusted, these individual temperatures. And you can see that up to about 12 lattice sites, subsystem sizes with 12 lattices, we can, this is a fit which we get. If you go to larger system size, I know that the largest one, which is plotted over here, this is now 20. What we do there is this, that we put in a parabola, we have a linear dependence and an offset, and what comes out is that it's only a parabola exactly proposed by Bisognano-Wichmann, and we could, of course, add a few more of these parameters, so we have to do a much more global parameterization. Very similar for the excited state over here. You can see that in the middle is sort of flat, which is what they expect for a thermal state. This is the region where you got volume law entanglement. The question is, what do I see at the board? I mean, do I see Bisognano-Wichmann? Because Bisognano really tells you that if I take an infinite system and I cut it in half, I should see a linear ramp. You can see that's not really linear, sort of is a little bit leveling down here. And in this boundary region over here, things go crazy, but this has to do with the fact that our variational wave function, is not very good when you go to the boundary over here. So we can, we understand these things very well, but you can see the onset of Bisognano-Wichmann over here, but then on the right-hand side in this boundary region, the statement is simply, we know what goes wrong here. It has to do with our state preparation, and it has very little to do with our measurement protocols that we have. So this is where the approximation in preparing the ground state now really comes in as an approximate thing. And this explains where some of these things go wrong. I could tell you now about fidelities with this verification that we have done here. As you can see, the black region here indicates do not believe the wave function over here and do not believe the wave function over here. And this is exactly where these things go wrong. But the rest, I mean, doing tomography in a many-body system, with a subsystem of 20, I think that's pretty impressive. We can talk about fidelities, but maybe I would like to skip that over here now for the moment. I can go back now and we can work out entanglement spectra if you want. We can measure central charge, which is pretty hard because it's small. It's only supposed to be 1. Well, we found 1.1 over here in our case. We can compare BQE circuits with the real ground states and the experiment, and they all agree pretty well. You would expect the BQE sort of to have a finite temperature relative to the real ground state. That's exactly what you see in this picture here. So there's a lot of technical details to be tested because for the system sizes, we can, of course, still do all of these calculations. Now, again, just a remark, how did we measure all of that, like obtaining an entanglement spectrum? So the statement is, in a many-body system simulator, we know how to measure entanglement spectra with these kind of protocols or ideas that I'm discussing. So this is sort of repetition of what I said earlier, we have data, we design the ansatz, Bisognano-Wichmann, we fit this data, take more data, and then we sort of verify the whole thing. This is what it was. And let me really emphasize that this is a sample-efficient tomography because we have only a relatively small number of parameters that we have to determine from the number of measurement data over here. normally this would be exponentially expensive. And if you want to read details over here, then you can do that in this review. The way that we do it at the moment does not scale in a sense of an polynomial scaling up to infinity, for the very simple reason that we have in our comparison theory and experiment, we have to do this exponent, and we do that using DMRG in 1D. We can do that. So there's one part over here that I will comment on these things and a little bit later, how we can, we might actually speed up. So there's an exponential computational bottleneck for very large system sizes beyond 20, which is far beyond the standard tomography, of course. Maybe you have to pay a classical computation price when we apply these protocols, but I'll comment on that later a little bit more. Well, here would be how we actually do that, but maybe I'll skip this slide over here. This is sort of randomized measurements. We do it in actually the de-randomized form over here. So we have described these things in our papers, and so there's ready to go protocols if you want to do that work not only in 1D, but also in higher spatial dimension. And this is the way how we obtained these data over here. Let me just add one more remark, and this has to do with the fact that I want to show you one theory slide where we take the generic system Hamiltonian of an ion chain. And here we plot the corresponding exact entanglement spectrum that you as a theorist might calculate. If you simulate this experiment, this is not an experiment now, this is a theory simulating an experiment and running the protocol on that, number of unitaries, number of measurements, sort of this is the number of runs that we have to do in this experiment. These are the predictions, crossing a phase transition, this phase transition that you have in this transverse Ising model over here, and the prediction for the corresponding entanglement spectrum. And this works amazingly well. But actually, the reason for showing you this plot has to do with the fact, how many experimental runs does it take if I do simple tomography, and then you can see as a function of the subsystem size, which is down over here, this is a total number of experimental runs. If you do tomography, it really blows up here exponentially. And if you do it in a different form, this is a low-rank tomography over here. And our way of doing these things gives this very flat dependence. So it's almost independent of the system size when we do our form of the entanglement Hamiltonian tomography, where we simply go in with the statement, well, Bisognano-Wichmann tells us what we should expect, and we can test and verify that afterwards. That's sort of the main message over here. We can do actually more things, and this is fun, and this is sort of approaching the point where I don't know really much about the corresponding physics. Maybe some of you have heard the so-called entropic forces. If I take an ion chain over here, I calculate, produce on my machine the ground state. I can also look at entanglement Hamiltonians of disjoint regions over here, And then what turns out is that you no longer get parabolas, but they are slightly distorted. And this tells you about so-called entropic forces. There are some papers out there that make a connection between, gravitational forces and relativity that we have in general relativity, maybe arising from entropic forces. That's beyond my pay grade, I would say. But we can do entanglement Hamiltonian tomography for disjoint regions and study all of that as a function of the distance over here, seeing exactly what people discuss as entropic forces in this context. And I just leave it with a statement over here that we know how to do that. And we indeed see long-range entanglement forces or terms over here in the entanglement Hamiltonian that correspond to what this whole community discusses. And so there's a final little bit of crazy comment, this relation of what we do with holographic gauge and gravity duality. All of you know, I guess, about CFD and ADS. What you do there is this, that you have here this ADS theory, in 2+1 dimension, and on the boundary you got your conformal field theory. Of course, entanglement in this context is related to the geometry. There's this famous relation. Let me just make the simple blunt statement. We, with our quantum simulator, sort of sit at the boundary over here. We can represent this thing here, and it is the entanglement structure of our wave function. This is the one that we know how to analyze, that represents sort of this additional degree of freedom over here that in this context here would correspond to an RG flow that goes from the UV here to the infrared. So there's some very deep relations. With the things that we are doing, we are kind of opening the ground for experimental investigations along these lines by providing the corresponding protocols that one could, investigate or maybe test and some of these things. But of course, the underlying physics, why you want to do that, is really quite a different story and motivation. And I wrote some of the references down here. And of course, fundamentally, this is related to Giffey-Vidal's MERA, which is making a tensor ansatz, which is here valid in this case. So let me conclude my talk here with just a few remarks. We know how to measure entanglement spectra, the Schmidt decomposition, not only for ground states, but we can also do that for quench dynamics. As a matter of fact, conformal field theory makes certain predictions there. Sadly, the experimentalists are not able to do quench dynamics in this regime, but we can nonetheless try it. And I want to show you from an old paper that this works amazingly well, even when it's not supposed to work. And I will conclude then with just one slide on quantum variational learning, where you overcome this bottleneck of classical post-processing, taking this exponential in the Gibbs ensemble, as we do it at the moment, by making quantum post-processing to do a spectroscopy of the entanglement Hamiltonian. So just very short remarks on that. What we do over here is this, that Rainer Platt and Christian Roos have done a long time ago an experiment. This is where we first, did these random measurement ideas in a completely different context. We were interested in Rayleigh entropies. But having all of this data around, we can simply apply this idea that we make a local ansatz for the entanglement Hamiltonian and try to find out if during quench dynamics, this is a quench dynamics, time is proceeding over here, how this Schmidt decomposition that we have over here, to see the buildup of the product state from a product state over here. You can see the lambda. This is this Schmidt value over here. It's here 1 is 1. All of the other ones are 0. When the quench is going on from the left to the right, this is theoretical calculations. You can see the entanglement spectrum building up until it finally will thermalize, for very long times. When we do that, then this is the agreement that we get, which is fantastic, and even though it's the local ansatz is from a theoretical point of view not really justified, it just works. And let me also just add one comment here. We have an error mitigation technique behind what we do with this Hamiltonian tomography, but I don't really want to talk about this. So there's a lot of technical things that I don't mention, but you can see that this agreement is fantastic. And you can also get here the entanglement spectrum out, and you get incredible agreement between theory and experiment. And sort of finally, let me make the remark that we can develop algorithms where we're not making measurements, and from the measurement then sort of like in this tomographic sense, find out what the entanglement Hamiltonian is by our sample efficient ansatz. But we could also try to do in situ on a quantum simulator, for example, apply quantum circuits. And for example, the idea that we had here, this is a paper now published some time ago, but it would maybe be great if somebody tried to do an experiment along these lines. We know that, so if I take my reduced density matrix from over here, from this region, and I time involve it with entanglement Hamiltonian per se, well, since rho A by itself is e to the minus, the entanglement Hamiltonian, the time evolution of that should be constant, okay? And we know that this, according to Bisognano-Wichmann, that this entanglement Hamiltonian here should be just a deformation of the original Hamiltonian. So experimentalists can in principle implement this time evolution here by simply preparing, and then switching over to a deformed Hamiltonian, taking this as a variational parameter. And they find then the point, they find this variational Hamiltonian or approximation of the entanglement Hamiltonian basically by monitoring any observables, like over here, at the very beginning is oscillating a lot, and at the end it gets flat. If you flat, then you're found and a variational approximation to the entanglement Hamiltonian. And these are procedures that are much, much more efficient in terms of finding the entanglement Hamiltonian and also doing an entanglement Hamiltonian spectroscopy sort of on this hardware level. And this is written on this physical review paper by Christian Cockerill et al. Bhuvanesh Sundar was also this paper, and a bunch of people from our group. So these are possible experiments that one could try to do in the future, and that will overcome this exponential bottleneck of this post-processing by doing a quantum post-processing in a variational way. So with this, I'm at the end of the talk here, and I just want to say that I've shown you theoretical ideas that we are able to implement directly in an experiment with a pretty big quantum simulator of 51 ions, running protocols for analysis of entanglement Hamiltonian tomography, and seeing, I guess, really for the first time, very fundamental features like these predictions by Bisognano-Wichmann for the ground state. And in this sense, I've talked here about entanglement Hamiltonian learning. I could tell you a lot about also Hamiltonian learning, not entanglement Hamiltonian learning, but if you want to read that, you should really maybe go to this recent article that we wrote last year as a perspective in Nature about where maybe quantum simulation might go in the future. And I conclude here by showing you people, that are fundamentally involved. I mentioned these guys, Christian Cocker, Rick van Beinen, and Thorsten Sacher was also involved in this on the theory side, and of course on the experimental side. I want to mention particularly Manoj in the group of Rainer Platt and Christian Roos, who did these experiments, and all of these guys over here were involved one or the other way in developing some of the toolbox that took us many years, but it's finally working. Thank you.
Yeah, thanks for the great talk. Yeah, it was amazing. Let's see if there are any questions in the audience. But if not, we had many questions during the talk. Yeah, so I guess we can wrap up. Thanks again for the great talk, Peter. It was amazing.
Thank you very much for listening and for the invitation. Okay.